The central pressure of a hurricane is the number that tells you what the storm actually is, not the category on a graphic, not the colour on a forecast map. The pressure at the storm's core, the density of air at the centre of the heat engine, measured in millibars, recorded by reconnaissance aircraft flying through the eye wall in real time, and right now, for the storm bearing down on the northern Gulf Coast, that number has been falling faster than it has any right to fall. In the past 24 hours, the central pressure of this storm has dropped at a rate that places this event in the top 1% of all Atlantic hurricane intensity changes ever recorded during the satellite era. The last reconnaissance aircraft to penetrate the eye wall found a reading 10 millibars lower than the measurement taken 6 hours before it. The measurement before that was already 12 millibars lower than the one before it. Each advisory cycle for the past 36 hours has found a storm stronger than the previous advisory said it would be. Each upward revision has happened on the 6-hour cycle. Each revision has moved the official forecast closer to what the aircraft was already observing. That number, that pressure drop rate, is what this story is about. Not a wind speed on a graphic, not the colour of the storm on the television map, the raw, physical rate at which this system has been extracting energy from the Gulf of Mexico and converting it into organised atmospheric violence. By the time you understand exactly what that number means, where it comes from, what conditions have allowed it to happen, what it says about the ocean beneath this storm and the atmosphere above it, and the people and places in its path, you will understand why what is unfolding right now in the Gulf of Mexico is not simply a dangerous hurricane season story. It is something more specific and more instructive than that. It is the story of a system that has found everything it needs to become as strong as it can possibly become, in a window of time and in a body of water that has been changing in ways that make that outcome more probable than it was a generation ago. And it is arriving at a coastline in the next 24 to 36 hours, while emergency managers work the phones and reconnaissance aircraft bank into the eye wall and millions of people decide whether to stay or go. The hurricane season that forecasters issued outlooks for in the spring of 2026 was expected to be below average. A developing El Niño in the equatorial Pacific was expected to increase upper-level wind shear across the Atlantic development region, making storm formation and sustenance harder. Forecasters from Colorado State University, from the Climate Adaptation Center, from AccuWeather all projected somewhere between 11 and 16 named storms. A reasonable, below-average to average season, the kind of season where you watch the tropics but don't hold your breath every week. What the seasonal outlooks projected correctly was the storm count. What they could not project, because no seasonal outlook can, was what the Gulf of Mexico would look like on the day a storm entered it, and what that storm would find when it crossed into one of the world's most energy-dense bodies of ocean water. Seasonal averages do not make individual storms. Individual storms are made by specific configurations of ocean heat and atmospheric shear that exist at specific moments. And on the specific days this storm has been traversing the Gulf, what it has found beneath its centre is a body of water that is behaving like a reactor rather than a fuel supply. There are things the current news coverage is getting right. There is a major hurricane in the Gulf of Mexico. It is heading toward the northern Gulf Coast. Mandatory evacuations are in effect for coastal surge zones in Louisiana, Mississippi, and Alabama. The storm surge forecast for low-lying coastal areas is serious and potentially catastrophic. Contraflow traffic operations have been activated on major Louisiana interstates. FEMA has pre-positioned urban search and rescue teams. The National Guard is activated. All of that is accurate and all of that is necessary. What the coverage is not fully communicating is the gap. The gap between what the operational intensity forecast models projected 24 hours ago and what the NOAA-P-3 Orion reconnaissance aircraft is currently measuring inside the eye wall. The National Hurricane Center operates on 6-hour advisory cycles. Between those advisories, the aircraft flies penetrations of the eye wall, drops GPS drops-ons that measure temperature, humidity, pressure, and wind speed as they fall through the storm's core, and transmits that data back to Miami in near real time. And what those penetrations have been showing is a storm whose intensity has been consistently and significantly exceeding what the models predicted it would be at each point in its Gulf crossing. The last penetration found a central pressure of 928 millibars. The HWRF model forecast, made 24 hours ago, had the storm at 942 millibars at this point in its track. The HAFS model, NOAA's newest and most capable intensity forecasting system, the replacement for the HWRF, deployed after years of research specifically aimed at improving rapid intensification prediction, was closer but still running behind. The aircraft is not running a model. It is measuring physical reality directly. The gap between model output and aircraft measurement is not rounding error. It is 10 to 15 miles per hour of maximum sustained wind speed in the storm's current state, and the pressure is still falling. To understand why, you have to go below the surface, not metaphorically. The story of this storm's intensification begins approximately 120 meters below the surface of the Gulf of Mexico, in a layer of warm seawater whose existence most hurricane coverage never gets around to explaining, and whose depth is the specific physical factor that is allowing this storm to do what the models said it probably wouldn't do. A hurricane is a heat engine. That is not a simplification. It is the precise physical description of the process. The storm takes heat energy stored in the ocean surface, transfers it into the atmosphere through evaporation, allows the moisture-loaded air to rise, condenses it into the towering convective walls of the eye wall and spiral bands, and in doing so releases the latent heat that drives the circulation. The exhaust, the spent energy, exits through the upper-level outflow, the cirrus clouds and anticyclonic winds that spread outward from the storm's top. The fuel for this engine is not just the temperature of the water's surface. It is the total amount of heat energy in the water column from the surface downward, what oceanographers call ocean heat content, measured as the integrated thermal energy from the surface to the depth, at which the temperature falls to 26 degrees Celsius. This number matters because of what happens to the ocean when a hurricane crosses it. Every hurricane stirs the water beneath it. The vortex of surface winds spinning over the ocean drives a process called Ekman pumping, which draws water upward from below the surface layer. And in a typical ocean column, the warm surface water sits over progressively colder water at depth, and when a hurricane stirs this column, it pulls cold water upward to meet the warm water at the base of the storm. The ocean cools itself from below. The fuel supply diminishes. The storm, if it tracks slowly enough, or if the warm layer is shallow enough, can actually cool the water beneath it to the point where it begins to weaken its own intensification. This is the natural governor that prevents most hurricanes from reaching their theoretical maximum intensity. It is the reason that a warm surface temperature, while necessary, is not sufficient to produce extreme intensification. The depth of the warm water matters as much as the temperature of its surface. The Gulf of Mexico is home to one of the most powerful oceanographic features in the Western Hemisphere. The loop current flows northward from the Caribbean through the Yucatan Channel, makes a broad arc into the central Gulf, then curves eastward and exits through the Florida Straits, where it becomes the Florida Current and eventually the Gulf Stream. It is not a surface feature. It is a column of warm Caribbean water that penetrates the Gulf to depths of 150 to 200 meters, bringing with it heat energy that the Gulf's own seasonal warming cycle would never generate to that depth on its own. As the loop current moves and fluctuates, it periodically sheds warm core eddies, rings of warm water that pinch off from the main current body, detach, and drift slowly westward across the Gulf basin. These eddies can be 200 to 300 kilometers in diameter. They maintain their temperature and depth structure for months after separation. They are invisible from the surface and from a boat. The water above them looks and feels like normal Gulf water, but satellite altimetry, which measures the very slight elevation of sea surface height that occurs above warm water due to thermal expansion, can detect their location and track them with precision. The current storm has been passing over one of these warm core eddies for the past 18 hours. Satellite altimetry data and data from NOAA's Argo float network place the eddy's center directly under the storm's track. The depth of the 26-degree isotherm, the boundary below which the water is too cold to fuel meaningful intensification, is approximately 120 meters under the current storm position. When the storm's vortex stirs the ocean beneath it, it does not find cold water at 40 meters depth. It does not find cold water at 80 meters depth. It stirs through warm water and more warm water all the way down to depths where the fuel supply simply does not run out on the timescale of the storm's crossing. The ocean heat content values being estimated from current altimetry data for the area beneath this storm are tracking at values comparable to those measured before Hurricane Ida underwent its catastrophic rapid intensification in August 2021. Ida passed over a loop current eddy of similar depth and temperature profile. In 24 hours over that eddy, Ida went from Category 1 with 85 mile per hour winds to Category 4 with 150 mile per hour winds. It made landfall on the Louisiana coast with a landfall intensity that produced measured wind gusts of 172 miles per hour at Port Fourchon before the anemometer failed. The current storm entered the Gulf with a higher initial intensity than Ida had at that stage. It has been over comparable ocean heat content for a longer continuous period. The physics have very few reasons to produce a different outcome, but ocean heat content is the fuel. Whether the engine can run efficiently depends on what is happening in the atmosphere above the storm. And in the atmosphere above this storm, conditions are as favourable for intensification as they can physically be. Wind shear is the atmospheric variable that most directly governs hurricane intensity. It describes the difference in wind speed and direction between the lower and upper troposphere, roughly between 1,000 and 200 millibars of altitude. A hurricane's convective structure depends on maintaining a vertically coherent vortex. The eye wall, the wall of the most intense thunderstorms surrounding the calm eye, must be able to stand vertically from the ocean surface to the upper troposphere. When upper-level winds are blowing in a significantly different direction or at a significantly faster speed than winds at lower levels, those upper-level winds catch the top of the vortex and shear it sideways. The warm core at the storm's center is ventilated with cooler, drier environmental air. The convective organization breaks down. The storm weakens, or at least cannot intensify. Low shear allows the vortex to stand straight. The eye wall convection organizes without being disrupted. The warm core deepens. The heat engine runs at maximum efficiency. For the past 48 hours, as this storm traversed the southern and central Gulf, upper-level wind shear along its track corridor has been below 10 knots, the threshold tropical meteorologists consider favourable for intensification. This is not a normal condition for early hurricane season in the Gulf. Shear in the Gulf's atmospheric environment fluctuates significantly from week to week, and the combination of low shear and deep warm water existing simultaneously and directly in the path of an active storm is not guaranteed. It is a coincidence of conditions that must align. In this case, they have aligned nearly perfectly. The reason shear is so low right now traces directly to a weather pattern that has been affecting tens of millions of Americans for weeks before this storm arrived. A strong mid-level ridge of high pressure, a heat dome centered over the southeastern United States, has been amplifying and holding position over Georgia, Alabama, and Mississippi since mid-May. This ridge has been the reason cities across the southeast have been posting heat index values above 110 degrees Fahrenheit for consecutive weeks. It has been the reason power grids across Gulf Coast states have been running at near maximum capacity under sustained peak demand for an extended period. The heat dome has been a human story about energy bills and heat stroke advisories and air conditioning failures. But the heat dome is also an atmospheric structure. At upper levels, it pushes the jet stream and the associated upper-level wind patterns northward, away from the Gulf. In doing so, it creates a region of relatively slack upper-level flow over the Gulf's surface, precisely the low shear environment that allows a hurricane's inner core to organize without interference. The heat dome that has been making life dangerous on land has been simultaneously clearing the atmospheric highway over the water, removing the one braking mechanism that might have kept this storm from using all the fuel the ocean has provided. The warm ocean and the warm atmosphere and the ridge that connects them are not three separate phenomena. They are three expressions of a single large-scale pattern. The same heat that raised sea surface temperatures in the Gulf raised air temperatures over the southeast. The same atmospheric blocking that built the ridge that created the heat dome that stressed the power grid also suppressed the wind shear that would have governed the storm's intensity. These systems are connected in ways that compound rather than cancel. Now look inside the storm itself. The reconnaissance aircraft flying penetrations of the eye wall is not merely measuring pressure and wind speed at flight level. It carries airborne radar systems that map the three-dimensional structure of the storm's inner core with the same kind of detail that a medical imaging system provides for the interior of a human body. And what those radar images have been showing in the past 12 hours is a storm whose internal architecture has organized into a configuration that tropical meteorologists recognize as a precursor to the most violent phase of intensification. The eye, the calm, roughly circular region at the storm's center, has cleared to a diameter of approximately 20 miles. GOES East infrared satellite imagery shows a well-defined eye with a sharp boundary. The eye wall surrounding it contains convective towers reaching 50,000 feet or higher, thunderstorms of a scale and intensity that dwarfs anything in normal atmospheric experience. The spatial organization of the eye wall convection matches what intensity algorithms trained on historical RI events identify as a high probability intensification state. There is also something more specific in the radar structure that introduces the most consequential uncertainty in the storm's final intensity forecast. The eye wall may be in the early stages of an eye wall replacement cycle. This is a process that is simultaneously one of the most fascinating and one of the most forecast critical events in tropical meteorology, and understanding it requires understanding the specific physics of how a hurricane's inner structure evolves under extreme intensification. As a hurricane intensifies, the eye wall contracts. The ring of most intense convection tightens inward toward the eye, driven by the dynamics of the vortex conservation of angular momentum. A figure skater who pulls their arms toward their body spins faster. The eye wall contracting toward the eye accelerates the winds near the storm's center in the same way. Maximum sustained winds increase. The storm grows stronger. But the contracting eye wall also suppresses the convection in the outer rain bands, cutting off their moisture supply and their access to upward motion. the outer rain bands begin to reorganize into a new convective ring, further out from the center, competing with the original eye wall for the storm's energy supply. For a period of anywhere from 6 to 36 hours, the storm has two eye walls. The original inner eye wall begins to weaken as the outer one strengthens. During this transition, the storm's maximum sustained winds may plateau or very slightly decrease. Then, as the outer eye wall contracts and the inner one dissipates completely, the storm often re-intensifies, sometimes to higher intensity values than it reached before the cycle began, now with a larger overall wind field that drives a larger storm surge footprint when it reaches shore. The reconnaissance data and the satellite imagery suggest this storm may be entering this process right now. If it is, there could be a window of 6 to 12 hours during which the storm appears to steady or slightly weaken. This window could be mistaken for a genuine and sustained weakening trend. And if it is an eye wall replacement cycle rather than a genuine weakening, the period of apparent steadiness will be followed by another burst of intensification, potentially bringing the storm to Category 4 or higher before landfall. The difference between Category 3 and Category 4 at landfall is not a marginal difference. It is the difference between winds of 130 miles per hour and winds of 145 miles per hour. It is a storm surge that is 2 to 4 feet higher across the entire coastal affected area. It is the difference between structural damage that primarily affects older construction and widespread structural damage to construction of all vintages. It is the difference between a levee system operating within its design envelope and one operating near the upper edge of it. The answer to the question of whether this storm's radar signature represents an incipient eye wall replacement cycle or a genuine intensity plateau is a question that the best operational forecast systems available cannot resolve from current observations with certainty. The inner core dynamics that drive eye wall replacement cycles operate at spatial scales of a few kilometers and evolve on temporal scales of hours, smaller and faster than most operational model grids can accurately resolve. The reconnaissance aircraft provides observational snapshots, but even those snapshots are separated in time by the hours it takes to fly the penetration pattern, transmit data, and process it. The storm's inner core is evolving between observations. This is the specific place where the science encounters the limit of what it can currently tell us with confidence. It matters enormously for the guidance being used to drive life and death decisions for millions of people over the next 12 to 24 hours. There is a second threat embedded in this storm that is not on the surge maps. It is not in the mandatory evacuation zone calculations. It has not been prominently featured in the emergency management communications reaching communities in the storm's path. It is, in terms of total storm-related mortality over the days following landfall, potentially as consequential as the surge and wind story receiving primary coverage. It is the moisture content of this storm, the total amount of rainfall this system is carrying, and the specific conditions of the watershed systems it will cross after it comes ashore. The Gulf of Mexico in 2026 is running at sea surface temperatures 1.5 to 2.5 degrees Celsius, above the 1991 to 2020 climatological baseline across much of the central and eastern basin. That temperature anomaly is the direct driver of the intensification story that has been covered. But it is also the driver of a rainfall story that has received far less attention. The relationship between ocean temperature and atmospheric moisture content is governed by the Clausius-Clapeyron equation, one of the fundamental relationships in atmospheric thermodynamics. For every degree Celsius of temperature increase, the atmosphere can hold approximately 7% more water vapor at saturation. With Gulf temperatures running 2 degrees above normal, the air feeding this storm is loaded with roughly 14% more precipitable water than it would carry if the Gulf were at climatological baseline temperatures. That 14% is not an abstraction. Translate it into rainfall, and it is the difference between a storm that drops 15 inches and a storm that drops 18 inches. Over a watershed system running at normal antecedent conditions, that difference is significant but manageable. Over a watershed system that entered storm season already saturated from a wet spring, that difference can be the margin between flooding that stays within existing drainage capacity and flooding that escapes it. The spring of 2026 in the Gulf Coast states was wetter than average. Soil moisture content across the lower Mississippi Valley, the Pearl River Basin, and the Mobile Tensor watershed system was running above the 75th to 80th climatological percentile entering the late spring. Several major river systems feeding into the northern Gulf were already at above normal stages. The Pearl River at Jackson, Mississippi, the Leaf River at Collins, the Chickasaw at Leakesville, the tributaries of the Alabama and Tombigbee rivers feeding into Mobile Bay from the north and east. These systems had little to no surplus storage capacity remaining before the storm. When 20 to 25 inches of rain, the central estimate for the rainfall accumulation beneath and to the east of this storm's track, falls on watershed systems that are already running at high water, the result is not additive. The rainfall cannot be absorbed at normal rates by ground that is already saturated. It runs off immediately into drainage channels that are already carrying high water. River stages that were above normal before the storm rise to record or near record levels during and after it. The inundation that results extends not just over the immediate floodplain, which would flood under any circumstances, but over secondary and tertiary drainage areas that are well outside the mapped 100-year floodplain. In August 2017, the Hurricane Harvey made landfall on the Texas coast as a Category 4 storm near Rockport. It then weakened rapidly and stalled over southeastern Texas, producing a rainfall event that reached 60.58 inches of accumulation near the community of Nederland, the highest tropical cyclone rainfall ever recorded in the United States. The direct death toll from Harvey was 107 people. Of those deaths, the overwhelming majority were caused not by storm surge and not by wind. They were caused by freshwater flooding in areas that were not in the official surge zone and had not received mandatory evacuation orders. People trapped in vehicles attempting to drive through flooded roadways. People who drowned in their homes in neighborhoods that were assessed as low surge risk. Communities that had made the rational calculation, not in the surge zone, in no evacuation order, therefore safe to shelter in place, and found that calculation was wrong because the event they were in was not principally a surge event. The current storm is not Harvey. It is moving faster. It will not stall for days over one location. But the rainfall loading it carries, amplified by Gulf temperatures running above baseline, is being forecast at 20 to 25 inches across the interior Gulf Coast, with localized totals that could exceed 30 inches in areas where topographic enhancement or slower post-landfall storm movement concentrates the precipitation. And it is falling on basins that have no surplus capacity. Communities 50 miles inland, 60 miles inland, 70 miles, places like Hattiesburg, Mississippi, Columbia, Waynesboro, the eastern suburbs of Jackson. These communities are not in a surge zone. They are not under mandatory evacuation orders. Emergency messaging has correctly communicated to them that the major immediate risk from the storm is along the coast. What the messaging has not communicated with equal force is that the rainfall these inland communities will receive, 15 to 20 inches, falling over 12 to 18 hours, on already saturated ground, draining into already elevated river systems, can produce flooding events that have nothing to do with surge and everything to do with water that simply has nowhere to go. The Pearl River has flooded Hattiesburg before. It flooded in 2020 under a rain event that was not associated with a tropical system at all, just a slow-moving frontal system that dropped concentrated rainfall on a wet watershed. That flood crested at levels that had not been observed in decades. The current storm is being forecast to drop more rain more quickly on a watershed in worse antecedent condition than existed in 2020. This is the hidden story inside the storm's moisture content, not hidden by deception, by the structural reality that emergency communications are organized around the surge and wind framework, because that framework has historically been the most effective way to motivate coastal evacuation behavior, which saves the most lives in the immediate post-landfall period. The inland freshwater flooding story is harder to communicate because the exact locations of worst impact are highly uncertain. The timing is 12 to 48 hours post-landfall rather than at landfall, and the affected communities are not psychologically primed by decades of Gulf Coast hurricane culture to recognize freshwater flooding as a direct hurricane threat. The storm is not happening alone. In the 72 hours before expected landfall, a separate upper-level trough moving across the central United States, entirely unrelated to the Gulf hurricane in terms of physical causation, has been producing a major severe weather outbreak across Texas, Arkansas, and Tennessee. The Storm Prediction Center issued a particularly dangerous situation tornado watch for portions of North Texas and the Dallas-Fort Worth metropolitan area 48 hours ago. Dozens of tornadoes have been confirmed across a corridor stretching from the Dallas suburbs to the Nashville metropolitan area. Multiple fatalities have been reported. FEMA has been activating disaster response resources for tornado-impacted communities in Texas and Arkansas, even as it is pre-positioning hurricane response assets for the Gulf Coast. The connection between the severe weather outbreak and the Gulf hurricane is coincident, not causal. They are driven by separate atmospheric features, but their simultaneous occurrence creates a compound emergency management challenge that is directly relevant to the hurricane response in ways that do not appear in any individual storm's impact assessment. The National Guard forces of Texas, Arkansas, and Tennessee are engaged in tornado response in their own states. The utility emergency mutual aid crews that would normally be pre-positioned along the Gulf Coast for rapid power restoration after the hurricane are partially committed to post-tornado damage repair in Arkansas and Tennessee. The total inventory of aerial search and rescue assets operated by FEMA, the Coast Guard, and the Air National Guard, helicopters, fixed-wing search aircraft, is under simultaneous demand from active search and rescue missions in tornado-affected areas and the imminent need for the same assets in post-Hurricane Gulf Coast operations. Emergency management is a finite resource problem. Every piece of equipment, every trained crew, every pre-positioned cache of emergency supplies that is being used somewhere else is a piece of equipment that is not in the pre-landfall staging areas along the Gulf Coast. This does not mean the response will fail. It means the response is beginning from a reduced starting inventory precisely at the moment when maximum inventory is needed. The compound nature of this crisis is compounded further by what the heat dome has been doing to the Gulf Coast's power infrastructure. The same atmospheric pattern that built the ridge that collapsed sheer above the storm has been driving record heat across the southeast for weeks. Power consumption in Louisiana, Mississippi, Alabama, and the Florida Panhandle has been at near-peak levels continuously since mid-May, operating transformers and transmission equipment at near maximum capacity under sustained thermal stress for an extended period. Grid equipment running at thermal limits is more vulnerable to physical damage. A transformer that has been operating at 95% of its rated capacity during weeks of 105-degree ambient temperatures accumulates internal thermal stress that is not reversed overnight. The insulation degrades marginally. The cooling systems cycle continuously. When the hurricane's winds arrive and begin physically damaging transmission infrastructure, snapping poles, tearing lines, throwing debris into substations, they will be hitting equipment that has already been weakened by the thermal load it has carried into the storm. Power restoration timelines that would normally be estimated in days for a major landfall may extend into weeks for portions of the grid that have been running at the edge of their thermal ratings. To the east and south of the coastline, the offshore oil and gas infrastructure of the Gulf of Mexico has been executing emergency shutdown procedures for 48 hours. The Gulf's offshore fields account for approximately 15% of domestic US crude oil production. The roughly 1,400 active structures in the Gulf, production platforms, floating production facilities, spar buoys, have been evacuating non-essential personnel by helicopter and supply boat since the storm entered the 72-hour forecast window. Well valves are being closed. Production facilities are being shut in. The 45,000 miles of submarine pipeline crossing the Gulf floor, the network of gathering lines, export lines, and deep-water tiebacks that moves crude oil and natural gas from wellhead to shore, cannot be evacuated. Its vulnerability to storm damage depends on the sea states the storm generates as it passes, which depend on the storm's intensity and track. After Hurricane Ida in 2021, the offshore industry shut in approximately 97% of Gulf production at the peak of the event. Some production facilities sustained structural damage and remained offline for weeks to months. Pipeline inspection after major events is required before production can resume through any line that may have been affected by extreme current or wave action on the seafloor. The submarine inspection process, conducted by remotely operated vehicles covering thousands of miles of pipeline, takes weeks. During that period, curtailed production contributes to regional fuel supply disruptions that manifest in price impacts for consumers across the Gulf South, the Southeast, and eventually nationally. This offshore disruption is already priced into the current emergency calculus. It is expected. What is less expected, because it involves a timeline that extends beyond the immediate storm response, is what the interruption of the petrochemical manufacturing corridor along the lower Mississippi River means for supply chains that depend on it. The stretch of the Mississippi River between Baton Rouge and New Orleans is home to the highest concentration of petrochemical and refining infrastructure in North America. This corridor of refineries, chemical plants, and industrial manufacturing facilities produces materials that feed into the supply chains of industries across the entire country: plastics, fertilizers, industrial chemicals, refined petroleum products. Facilities in this corridor are executing emergency shutdown procedures right now, preparing for the combination of wind and surge and flooding that a major Gulf Coast landfall produces. Some will be able to restart within days of the storm's passage. Others, if floodwaters reach their process equipment, will be offline for weeks or months. The downstream supply chain effects of extended downtime for this corridor take time to manifest. They are not the story of a hurricane landfall. They are the story of the weeks after. When the immediate emergency is over, the water has receded, and industrial supply managers are discovering that the feedstock they assumed would be available is not. New Orleans sits in a bowl. The city's average elevation is approximately 6 feet below sea level, a consequence of natural delta subsidence and the management of the Mississippi River for navigation and flood control over the past century. It is protected from hurricane surge by the post-Katrina flood protection system, 350 miles of levees and concrete floodwalls, massive surge barriers across the Lake Borgne Inlet, and the MRGO navigation channel, pump stations capable of moving billions of gallons of water per day, engineered and built at a cost of approximately $14.5 billion, the largest civil works project in United States history. The system performed under Hurricane Ida. Ida was a powerful Category 4 storm at landfall, one of the strongest to have ever struck Louisiana. The levee system held. No water came over the protection perimeter. The city inside the levees did not flood from surge, but the design of the protection system, the dimensions of the levees, the heights of the flood walls, the capacity of the surge barriers, was calibrated to a specific set of storm scenarios, derived from statistical analysis of the historical record of Gulf hurricanes and their surge profiles at the New Orleans Basin. The design standard is frequently described as protection against the 100-year surge event. What that means in physical terms is a surge profile calculated from the statistical distribution of Gulf hurricane surge events that characterize the late 20th century, the historical period of record that engineers had available when the design specifications were developed. The exact surge profile that any given storm produces for any given protection segment depends on storm intensity, storm size, track, forward speed, and the precise angle of approach. A storm on a track that places its center 50 miles to the east of Ida's produces a different geometric loading on different segments of the protection perimeter than Ida did. Certain segments, the eastern flank of the St. Bernard Parish levee system, the north shore along Lake Pontchartrain, see higher surge loads from an eastern track than from a direct or western track. The current storm's projected track places its center in a range that is being actively evaluated by Army Corps of Engineers hydrologists in real time. The surge heights being modeled for a Category 4 landfall on the current track are within the design envelope, but not with the comfortable margins that existed for Ida's track. If the storm intensifies further before landfall, if the eye-wall replacement cycle currently showing in the radar resolves into another burst of intensification rather than a genuine plateau, the surge calculations change. The difference between Category 4 and Category 5 surge is not linear. Surge height scales approximately with the square of wind speed. A 15 mile per hour increase in maximum sustained winds does not add 15% to the surge. It adds more. To the east, Mobile Bay amplifies surge through basic geometry. When a hurricane approaches from the south or southwest, which is the approach geometry for a storm on the current track, the winds on the storm's right front quadrant push enormous volumes of water northward into the bay's open mouth. The bay narrows progressively as it extends northward toward the city of Mobile. The water driven into the bay mouth cannot spread laterally. It piles up, it rises. After Hurricane Frederick made landfall near the Alabama-Mississippi border as a Category 3 storm in 1979, the surge recorded at the northern end of Mobile Bay reached 15 feet. The current storm, if it makes landfall at Category 3 or higher intensity to the west of Mobile, which the current forecast cone encompasses, will drive its right front quadrant surge directly into the bay. NWS Mobile is modelling surge heights of 12 to 16 feet at the head of the bay for the range of intensities and tracks currently in the forecast uncertainty envelope. The downtown Mobile waterfront sits at elevations of 5 to 10 feet above sea level. The major traffic arteries running along the northern shore of the bay, the infrastructure needed for emergency response and eventual recovery, run at similar elevations. The wastewater treatment infrastructure at the bay's northern terminus, the facility that processes sewage for a large portion of the Mobile metro area, is located at an elevation that makes it vulnerable to the upper end of the current surge forecast range. If that facility floods with salt water, the resulting service disruption and decontamination requirement is a post-storm public health problem measured in weeks, not days. East of Mobile, the Florida Panhandle adds a dimension to this event's total impact that civilian emergency communications rarely address directly. Naval Air Station Pensacola, the home of naval aviation training, the base from which the Blue Angels fly, sits on the western shore of Pensacola Bay, exposed to storm surge from a storm on the current track. Eglin Air Force Base, the largest Air Force installation in the world by land area, extends across portions of Okaloosa, Walton, and Santa Rosa counties in the Florida Panhandle. Both installations have been executing storm preparation procedures for days, moving aircraft to inland bases, securing outdoor equipment, pre-positioning response assets. The aircraft can be flown to safety. The infrastructure cannot. Hangar buildings, command facilities, fuel storage systems, ordnance storage facilities all remain in the storm's path. What are the scientists who track these storms actively uncertain about right now? The rapid intensification prediction problem is the most consequential scientific limitation in operational hurricane forecasting. It has been known for decades. Research programs have been dedicated to it. Significant progress has been made. The gap between track forecast accuracy and intensity forecast accuracy has narrowed over the past 20 years as better models, better data assimilation, and better physical understanding of inner core dynamics have been incorporated into operational systems. But for the specific phenomenon of extreme rapid intensification, for the storm that goes from Category 2 to Category 4 in 18 hours over a loop current eddy with minimal shear, the models still run behind the aircraft. The fundamental physical challenge is a scale mismatch. Rapid intensification is driven by the interaction of three physical systems operating on different scales simultaneously. The ocean heat content that enables RI occurs at the scale of hundreds of kilometers. The eddy under this storm is roughly 250 kilometers in diameter. The wind shear environment that allows RI to proceed occurs at the scale of thousands of kilometers. The ridge that has collapsed shear covers most of the southeastern United States. But the convective organization that actually triggers the intensification burst, the specific way the eye wall convection arranges itself, the location and timing of the convective bursts in the hot tower cells that spike through the upper troposphere above the eye, occurs at scales of a few kilometers and changes on timescales of minutes to hours. Operational forecast models run at horizontal grid spacings of 3 to 6 kilometers for the inner domain. At those resolutions, they can represent the general structure of the eye wall, but they struggle to accurately represent the specific convective processes inside it that determine exactly when and how fast intensification occurs. The reconnaissance aircraft measures reality at a point in time. The model integrates forward in time from an initial condition. When the initial condition does not perfectly represent the inner core convective organization, because the model cannot fully resolve it at any grid spacing currently computationally feasible in real time, the model diverges from reality, and the divergence compounds with time. NOAA's half-S represents a significant improvement over its predecessor for intensity forecasting in most situations. For this specific storm, at this specific moment in its intensification, it is running 10 to 15 miles per hour behind the aircraft. That 10 to 15 miles per hour is the difference between the current official forecast and what the reconnaissance is actually observing. Each advisory cycle, the NHC has been adjusting the forecast upward. The forecast is catching up to physical reality. It has not caught up yet. The loop current eddy observing problem is a separate gap. Satellite altimetry provides accurate location and approximate temperature data for loop current eddies, but the altimetry data must be assimilated into the ocean model that is coupled to the atmosphere in the hurricane forecast model. Now, the assimilation pipeline from satellite measurement to ocean model initial condition has latency. Eddies in the modelled ocean are sometimes displaced in position or slightly wrong in temperature depth compared to where the altimetry actually places them. For this storm, the ocean model was placing the centre of the warm core eddy approximately 50 kilometres southeast of where the altimetry data and the Argo float observations suggest it actually is. 50 kilometres is the difference between the storm's centre spending 18 hours over the highest OHC portion of the eddy and spending 12 hours over it. 6 hours of additional time over peak OHC water is a significant difference in the total heat energy transferred to the storm during its crossing. And NOAA has been advocating for years for additional ocean-observing assets, more Argo floats, more glider deployments, more frequent altimetry satellite passes, precisely because of this specific problem. The operational hurricane forecast model is only as good as its ocean boundary condition, and the ocean boundary condition is only as accurate as the observing system that provides data for it. This storm is demonstrating that gap in real time. The rainfall and inland flooding uncertainty is the third major open question. The Weather Prediction Center's quantitative precipitation forecast for this storm projects 20 to 25 inches across the primary impact zone. That forecast is made with significant uncertainty. The actual rainfall for any given location depends on the exact storm track, forward speed, and internal convective structure, all of which are uncertain at the spatial and temporal scales needed for specific community-level impact prediction. Converting a rainfall forecast into a river stage forecast requires hydraulic modelling of specific watershed systems, including real-time representation of antecedent soil moisture and upstream river conditions. The combined uncertainty of the rainfall forecast and the hydrologic model means that the specific locations of worst inland flooding, the specific road crossings that will be underwater, the specific residential areas that will be inundated, cannot be predicted with confidence until the storm is close enough to landfall that the rainfall is actually beginning to fall. Communities in the potential inland flood zone are being asked to make shelter decisions based on official guidance that honestly cannot tell them at this moment whether their specific neighbourhood will see 2 feet of water or 8 feet of water in the 24 hours after the storm passes. That is not a failure of the forecast system. It is an accurate representation of the genuine scientific uncertainty. But it is a difficult message to act on. This storm is not an accident of coincidence. It is a member of a class that has been growing. The modern Gulf Coast hurricane record has accumulated, over the past decade, a series of events that share a recognizable signature. Storms that enter the Gulf in conditions that the operational forecasting system assessed as moderately favorable for intensification and that then exceeded those forecasts, and sometimes dramatically, by finding specific ocean features that the model ocean did not accurately represent in real time. Hurricane Ida, August 2021. The forecast 24 hours before landfall showed a Category 3 storm. The aircraft at landfall measured a Category 4 with 150 mph sustained winds. The difference between the forecast and reality was the specific loop current eddy Ida crossed, an eddy whose heat content was greater and deeper than the model's ocean field represented. Port Fourchon, Louisiana, measured 172 mph gusts before instrument failure. The communities on the southeastern Louisiana coast below the New Orleans levee system, Grand Isle, Galliano, La Rose, communities rebuilt after Katrina, sustained catastrophic damage. Hurricane Michael, October 2018. And Michael entered the Gulf as a tropical storm and underwent intensification that the operational models collectively underforecast. It made landfall near Mexico Beach, Florida, as a Category 5 storm with maximum sustained winds of 160 mph and a central pressure of 919 millibars, the third lowest landfall pressure ever recorded for a continental United States hurricane. Mexico Beach, a small panhandle community of approximately 1,000 permanent residents, was erased. The National Weather Service radar installation in Tallahassee, a 130-ton piece of equipment on a reinforced concrete tower, was taken offline by Michael's Passage. The final direct death toll was 74 people. September and October 2024 produced back-to-back catastrophes. Hurricane Helene, following a track through the eastern Gulf, underwent rapid intensification to Category 4 before making landfall near Perry, Florida. Its winds drove record storm surge into the historically protected Tampa Bay region, inundating waterfront communities that had not flooded in living memory. Its moisture-laden circulation then moved inland and produced freshwater flooding across the western Appalachians of North Carolina and Tennessee that killed more than 200 people in mountain communities. Towns like Asheville, North Carolina, and Irwin, Tennessee, where the concept of hurricane-related mortality had no cultural framework. People died in freshwater floods from a storm they knew had already made landfall hundreds of miles away. 3 weeks later, Hurricane Milton underwent one of the most extreme rapid intensification events in the Atlantic record, dropping approximately 100 millibars of central pressure in 24 hours over the Gulf, reaching a peak central pressure of 895 millibars, the lowest ever recorded for any storm in the Gulf of Mexico. Milton weakened before its Florida landfall near Siesta Key, but still struck the west coast of Florida as a major hurricane. 2 major hurricane landfalls on Florida's Gulf Coast within 13 days of each other. No close parallel in the modern record. The pattern visible in these events is not one of random extremity. It is a pattern of Gulf storms finding more energy than the forecasts predicted because the ocean delivering that energy has been consistently warmer, consistently deeper in its warm layer than the historical baseline from which those forecasts were constructed. The loop current eddy field has been more energetic. Marine heatwave conditions, anomalously warm SSTs persisting over extended time periods, have been more frequent and more intense. Research published in Communications Earth and Environment has documented that rapid intensification is approximately 50% more likely during marine heatwave conditions. The Gulf in 2026 qualifies as a marine heatwave environment in its central and eastern basins. What the Gulf's temperature record shows is not individual anomalous events. It shows a trend. The average sea surface temperature in the Gulf has increased by approximately 1 degree Celsius since the mid-20th century. The warming has not been uniform. The deeper warm layers associated with the loop current system have warmed more than the shallow western Gulf shelf. But the overall trajectory is unambiguous. The Gulf has more heat energy now than it did when the protection systems now guarding New Orleans were designed. More than when the levee setback elevations for the Mississippi coast were calculated. More than when the 100-year storm surge return period estimates used in infrastructure planning were derived. The infrastructure protecting the northern Gulf Coast was designed for the historical distribution of Gulf hurricane intensity. That distribution was a reasonable basis for design in the late 20th century. If the distribution has shifted, if what was once a 1 in 50-year age event over the Gulf is now occurring at 2 or 3 times the historical frequency, then the design standard for that infrastructure is less conservative than its designers intended. Not because the infrastructure was built poorly, but because the conditions it was built to protect against have become more probable. This is a calculation that every coastal engineer who works on Gulf Coast infrastructure understands at some level. It surfaces in professional discussions about updating design standards, about revising FEMA flood maps, about the costs and feasibility of additional levee height. It is slow work because construction is expensive and slow and requires political will and funding appropriations that move on timescales measured in decades. The ocean is not waiting for the political cycle. The storm is now within 24 hours of the coast. The evacuation orders that are currently in effect cover the coastal surge zones, the areas that slosh and ADCIRC surge. Modelling identify as inundation zones for storms of the forecast intensity range. Those orders have been going out for 48 hours. Contraflow is active on major Louisiana interstates. Shelters are opening in northern Louisiana, Arkansas, and Tennessee. The people who have received, understood, and are able to comply with those orders are in the process of leaving. But 3 categories of people are not fully reached by the current emergency communication. The first, coastal residents who have survived multiple Gulf hurricanes and have made the calculation, correct in many individual cases but wrong in the aggregate, that their specific home, their specific neighborhood, has survived before and will survive again. Survey data consistently shows that previous experience of surviving a hurricane in place increases the probability that a resident will decline to evacuate in subsequent events. The knowledge that their home withstood Ida leads some residents to conclude that it will withstand this storm. That conclusion does not account for the difference between a Category 3 storm and a Category 4, the difference between a near miss track and a direct hit, or the difference between a storm that is continuing to intensify and one that peaked before landfall. The second, low-income residents without vehicles and without the financial means to fund a multi-day evacuation, hotel rooms, fuel, food, who are physically present in the evacuation zone and have no practical means of leaving. This population is not making a choice to stay. They are facing a structural barrier. For these residents, the quality and capacity of the shelter of last resort system, the shelters opening in storm-resistant facilities in communities outside the surge zone, is the operative life safety question. The third, inland residents who are not in the surge zone have not received evacuation orders and believe that the hurricane's primary threat does not extend to their location. For some of them, that belief is correct. For others, those in the specific inland river basins where antecedent conditions are worst and where the storm track's rainfall band will be most concentrated, it may not be. The pressure inside this storm is still falling. The reconnaissance aircraft will fly another penetration in the next few hours. Whatever it finds will be transmitted to the National Hurricane Center, incorporated into the next advisory, and communicated through the emergency management chain to the public and the emergency managers trying to respond to it. That advisory may show continued intensification. It may show a plateau consistent with an eye wall replacement cycle. It may, if the outer eye wall has already substantially formed and the inner one is already collapsing, show a temporary modest weakening that will reverse. What it will not show is certainty. The uncertainty is not media hedging. It is not the National Hurricane Center being cautious. It is the honest reflection of the physics at the frontier of what the current science can resolve for this specific storm at this specific moment in its intensification history. The storm is operating at a scale and with an intensity that is testing the operational limits of the observing and forecasting systems designed to provide the guidance on which millions of people are now making decisions. The number this story began with, the pressure drop rate, the top 1% intensification event in the satellite record, is not a shocking number because it is unprecedented. It is a member of the distribution. The distribution has happened before. Ida happened, Michael happened, Milton happened. They happened to specific places, in specific years, under specific configurations of ocean heat and atmospheric shear that the scientific record now documents clearly. Each time, in the hours before landfall, the reconnaissance aircraft was finding a storm stronger than the model said it would be. Each time, the advisory was updated upward. Each time, the full weight of what the storm was arrived faster than the updated guidance had time to fully communicate. That number is what it is. The pressure is falling because the ocean beneath this storm has spent weeks, months, accumulating heat energy in a body of water that is warmer than it was a generation ago. It is falling because the atmospheric shear that should be governing the storm's intensity has been removed by a heat dome that is itself the product of conditions that go beyond any individual weather event. It is falling because the inner core of this storm has organized into a structure that indicates not the beginning of weakening, but the continuation of a process that is not yet complete. The coast is 24 hours away. The pressure is still falling.